Hello guys, today I'm going to explain you how can we solve this problem, maximum size of a set on a given directed acyclic graph. So this problem was asked in June 20 easy challenge on Hackerearth. The problem statement says that we are given a directed acyclic graph with n vertices and image, and we need to find possible subset there such that we can reach from every like if we take any two unordered pair, we can reach from one to other. So yeah, there are certain things like first we need to understand what an unordered pair it means. Like when we say an unordered pair like u comma v, we also consider v comma u as well. So if there is what we need to find is that a subset of vertices from this graph such that the every pair u comma v, if we take, there has to be a path between either u to v or v to u. So let's try to understand this by taking this example. There are three vertices and two edges, and these edges are 1 to 2 and 2 to 3. So if we draw this like this one, we have 1 to 2 and 2 to 3. So what are the possible pairs that we can pick? Let's say for example we pick this one, all right, and once we pick one, we can take two, because there is a path between 1 and 2. So we can easily say that we can take 1 and 2. All right, now can we take 3? So if we take 3 here as well, like if we do a union of 3 with our earlier set, can this be included? Let's see how. Yeah, 3 can be included because 3 can be reached from 2, and from 1 to 3 also it is possible, because we can go from 1 to 2 to 3. All right, so if you look closely, this problem is simply about finding the longest path that you can have in a directed acyclic graph. Why I'm saying so is because if what we are supposed to find is the largest possible subset such that between every pair we can move from the other way, move from one vertex to the other vertex. And let's say if you say that, hey, here we cannot move from 3 to 2 or 3 to 1 or 2 to 1, but that's what the problem statement has said that, and that is why it is a bit easier, because 3 to 2 is not possible, but 1 to 2 is possible. All right, so this being unordered pair, 3 to 2 is equivalent to 2 to 3. Now let's try to add one more node to our graph. Let's say we had one more node here where we can let me draw it here. So we have another node which we can reach from 3 to 4. All right, so let's say this is what we have. So can this 4 be included into our set? So I mean, to find the subset, what we always do is we trying to see if this can be included, I mean if this is a valid node into our subset or not. So if we take 4, will it still follow the same rule? Like can every unordered pair in this subset will have a path from each other? So if we have 4 into our group, the already defined group, so we can see that we can reach from 4, we can reach from every other node into our existing subset to 4. So now we can say that we have a subset now where we have 1 and we have 2, we have 3, as well as we have 4. So this is this is overall 4 length of subset that we have found till now. Now let's try to add one more node here. Once we add one more, let's say we added here, which we can reach from 1 to here, and let's call it node 5. So can this node 5 be included into our set or not? So to know whether 5 can be included onto our set or not, we'll try to see if from every node can we reach to 5 or not. So let's see, from 1 to 5 that is possible. From 2 to 5, is it possible? No, it is not possible. But from 5 to 2, is it possible? No, that is also not possible. So we have found an unordered pair 2, 5 where there is no path, or there is no edge that we can reach from one node to other node. So 5 cannot be included. However, 5 could have been included with 1, so that would have formed a set of 1:5, but that set is smaller than what we have. So this is what somehow gives us an idea about that we can start from each node and try to find what's the longest path that we can go from one node to the other node what's the longest distance that we cover starting from one node. Let's say if we started from 1, we could have ended with a path of one size if we go along this path, and if we continued on this one, we could have found 1, 2, 3, overall 4 nodes in this path. So this being 4 and this being 2 and this being 4, we will say that the longest that we can go from 1 is 4, largest size if we have 1 into our set. Now if we say that we start from 2, what's the longest that we can have? We can go from 2 to 3 and 3 to 4. So the longest subset we can have is 3. Similarly, from 3 and 4 you can check. So out of all of them, the paths from starting from 1 gives us the best answer. So based on this reasoning, now let's try to take another example and see how we can find the longest path in a given directed acyclic graph. Now let's try to see how we can find the largest path that we can achieve from one node. Let's say if we start from this node, what's the longest path that we can achieve from here? And this is very much similar to saying that the longest path that can be achieved from here plus 1 will be the answer for this one. So that means if we somehow find the best answer for its child node or its adjacent nodes, like for every node, if we are able to find the largest path for its adjacent node, we can just add plus 1 to the answer that we found from the adjacent node. So for example, similarly we can say for 2 we can have 2 different paths starting from here, or let me just say starting from here or starting from this path. So this would give us the longest path as 1, but here we will have again 2 options. This one will depend on this and this will give you back 2, and this will give you back this will give you back 1, 2, and this will give you back 1. So we'll compare 1 and 2 and we'll get 2 as the best answer, and we'll add 1 plus 2 here. So if we start from 5, we know that the answer is 3. Similarly, we'll for 2 we will then trace back and say that, hey, for 2 the options that we had was to traverse from 3 and for 5, but the best answer that we can get is from 5. So now we found that this is 3 is the best answer, so we will add 1 plus 3 and this becomes 4. Similarly, once we found that the only possible path from 1 was to go to 2, so we can just add it to 4 and the answer becomes 5. So that's the longest path that we can have here, 1, 2, 3, 4, 5. And now we will also keep all of these visited nodes marked, so that we can try to start from some node where we haven't visited yet, and that can happen if the graph is a disconnected graph. So let's say if we had some other graph which might have a better path. Let's say if this was just a simple cycle of each node connected to its adjacent node like this one, then here we'll see that we have a bigger one. So that's what we are going to do. We are going to traverse I think here also it's very much same, but I think you get the idea. There can be a disconnected graph, and if we just stop by getting the answer from one graph, that will not be the best answer. So we'll need to consider all the unvisited node in the graph, and then we'll need to find the answer for the best of them. So now once we have seen how we can do this, let's try to see how we can code this one. Alright, so as you can see that I have already solved this problem. I'll just walk you through my code. So I have created array of vectors to keep track of each edge. I mean, this is what my graph will be, and a boolean array to keep track whether a node is already visited or not, and then a dp array to keep the best answer for each node. I mean, the longest path that we can achieve from starting from each node. And then here I have just taken the input. I have initialized these two arrays. Like initially none of them are visited, so mark all of them unvisited, that false, and initially all of them have 0. And then what I'm doing here is I am just finding the first unvisited node. I mean, not only the first, I'll try to find all the unvisited node, then do a DFS from the unvisited node. And as I said, the answer for this particular node, the current node, will be the answer from the maximum of all the branches that we can have. Like so for example, if we take this particular case for 2, we had two different child here. From 2 we can go to 3, and we can go to 5, and what we will do is for each adjacent vertex from 2, we'll try to find the answer, and we'll compare both of them, then we'll get the maximum of age. So that's what I'm doing here. For each adjacent node from this given node, I'll check first that if this is already visited or not. If this is not visited, then I'll do a DFS, and then I'll try to find the answer for this one. And then the DP of this current node, that means the best answer for this current node will be the maximum of all the answers that we can have from all its adjacent nodes, and that's what I'm doing. And +1, because this current node can also be subset of can be part of the subset. Similarly here, once we will find the answer from all the nodes, we'll just compare what's the best answer that we can get from starting from each node, and then we will add +1 because we can have that particular node as well into our subset. So yeah, I hope I was able to explain you guys. Please let me know in the comment section if there is any doubt or any suggestion or any feedback or any comments that you have for me. Please let me know that in the comment section below, and please do not forget to subscribe my channel if you haven't already, and thanks for watching this video, guys.